Now that we have set our goal to study the effect of a force over space, and we also have the mathematical tool to do that, which is the scalar product, let's put it into use. Let's consider the case where a force F is applied on an object, and as a result, the object moves from a certain point, starting point, to the final point. And let's say here, this is the starting point I, and here's the final point F. And the path of the particle can be variable, and the force can also be variable. Now, everything starts from Newton's second law in classical mechanics. And so we're going to start again with Newton's second law, F equals ma, which is equivalent to F equals m dv dt, dv over dt. And then what I'm going to do is combine the effective force over displacement. Now we know a way to do that, and that is to take the dot product, right? And that makes sense because that would only consider the component with force along the direction of motion dr. So let's do that. Let's take the dot product of f dot dr, both sides of it. So f dot dr, and it's m dv over dt dot dr, right? That certainly works. Now, I'm going to rewrite the right-hand side a little bit. Instead of dv over dt, then dot dr. I can do that as dv dot dr over dt. That is, I'm going to move dt from beneath dv to beneath dr. That doesn't make any difference. So I have a new expression now on the right-hand side, and that is m dv dot dr over dt, right? Now we all know what dr over dt, that's just v. So I can further rewrite the right-hand side as m dv dot v, right? But this is not the end. We can further simplify that. What's dv dot v? Can we further simplify that? Well, the answer is yes. We're going to start with v dot v equals to d of equals v squared. Of course, you know it's equal to v squared, right? And then I'm going to differentiate both sides. Okay, I'm going to differentiate both sides. So let's do that. Let's do that. D of that. Now, the left-hand side, d of v dot v. What is that? When you differentiate a product, d of ab, isn't that equal to a dv plus b dA? Right? So I can rewrite this as v dot dv and then plus dv dot v. Right? Now, does it make any difference when I do v dot dv or dv dot v? That is a dot b versus b dot a. Are they different? No, they're not different. They're the same. So these two terms are equal to each other, which further makes it equal to 2 dv dot v. Right? But wait a sec. I know what dv dot v is. It appears here. It first appeared here. So I can replace dv dot v now as what? As 1/2 of dv squared. I'm simply going to equate, I'm just going to equate this with that, right? So that gives me the simplification that I'm looking for, which is dv dot v equals 1/2 d of v squared. There is no vector anymore. 1/2, of course, can be taken into the differential. So it's d of 1/2 v squared. At this point, I'm assuming the mass doesn't change. In fact, if the mass does change, F is not even equal to ma anymore. It's a new different, it's a more general expression you'll learn in chapter 9. So since the mass is a constant, I can take the mass m into the differential as well. So now the right-hand side can be rewritten as m dv dot v equals to d of 1/2 mv squared. Okay, took that 1/2 in, I took the m in, and v, as you know, dv dot v is the same as d of 1/2 v squared. Okay, so I'm going to equate this newest expression with the left-hand side, which is f dot dr. So let's see what we have now. So we have d of, we have F dot dr, that's the left-hand side, equals to d of 1/2 mv squared. At this point, I'm going to introduce a pair of new concepts. The left-hand side, which is the dot product of force and displacement, is defined to be the work done by the force F over displacement dr. So that's the work. So dw. It's an infinitesimal small amount of work, so it's dw. Define, okay, dw as F dot dr. That is the work done by the force F over the displacement dr. And the right-hand side, it's a differential of 1/2 mv squared. This expression 1/2 mv squared will appear many, many times everywhere in physics, actually. And we give it a name. We call it the so-called kinetic energy, K, sometimes called Ke. K standing for kinetic, 1/2 mv squared. So that's a pair of new definitions. Okay, so for the first time, we see the concept of energy in our course. This is not any energy. It is the so-called kinetic energy, otherwise known as the energy of motion. And that, of course, makes sense because you have to have speed v to have that energy. So it's the energy of an object in motion. Okay, so let me name those again. So this is work. W is work. And this is the kinetic energy. Okay, so with this new pair of definitions, I can rewrite the above formula as dw equals dk. It's just that simple, right? dw equals dk. Now, that is only what happens over the infinitesimally small amount of displacement. Suppose I want to look at the total effect from initial to final, okay, from this point A to point B, initial to final. Then what is the overall effect of this force? Then I have to integrate, right? So I integrate, then I get dw from initial to final equals what? dk from initial to final. Okay, now if I write it more explicitly, dw is F dot dr. So then I have I to F dot dr. What does that equal to? It equals to K final minus K initial, which is 1/2 m v final squared minus 1/2 m v initial squared. Okay, let me try to box this. And this is an extremely important expression that we just discovered. Okay, there we go. So this is derived from Newton's second law. See, we started out from Newton's second law at the very top, right? And we came up with this, with the new tool that we learned, which is the scalar product. So now we have answered this question. What is the effect of a force over space, or when the force is exerted on the object over a certain displacement? The effect is that it did work. How much work? Is the integral of this force dot dr. Okay, and this is W initial to final. That's the integral on the left-hand side. What is the result of that? The result is that you have changed the kinetic energy of the object from initial value to final value. And the change in kinetic energy equals to the work done by the force F, delta K. That is the right-hand side. Okay, so this is a shorter version of the formula above. Okay, this is a shorter version. Now, this is not a new law because everything is mathematically derivable from Newton's second law, which is truly a law. We don't know where it came from. But this one we know, it came from Newton's second law. Therefore, it is not a law anymore, we call it a theorem. What theorem is that? It is the so-called work energy theorem, okay? It makes sense, the left-hand side is work, the right-hand side is the change in energy. So this is so-called work energy theorem. So I'm gonna put the name here. It is a direct consequence of Newton's second law. It is derived from Newton's second law, but it looks quite different from the original form of F equals ma, doesn't it? Right? Again, Newton's second law tells you what happens at one moment. You give me the force at this moment, I can tell you the acceleration at this moment. In order to find the cumulative effect of a force over space, we have to integrate this F over the displacement from initial to final. So it links two states, initial and final state. And the result of that is that the force did work, and that turned into the change in the kinetic energy of the system. Okay, so that's the so-called work energy theory. And this is a rewritten version of Newton's second law. We're introducing a pair of new concepts, energy, more precisely kinetic energy and work. And we're introducing this new approach or new method, that is the work energy theorem. Turns out that in many occasions, this provides an easier answer than F equals ma in its original form. And you will see plenty of examples of that. So this is the centerpiece of chapter 7, the so-called work energy theorem. And what's left is really just applications of the work energy theorem. Okay, so we have the centerpiece right here, the work energy theorem. Before we can apply this new approach to solve problems, including the very first problem we posed at the beginning of chapter 7 without actually solving it yet, we have to know how to find the work done. Now, the right-hand side is very clean, right? 1/2 mv final squared minus 1/2 mv initial squared. There is no information in between initial and final. Just go from initial kinetic energy to final kinetic energy. That's it, very clean. But the left-hand side remains mostly dependent on the path that links initial and final state. It's the work done by the force going from initial to final state. You have to know how to do this integral, otherwise you still cannot solve the problem with the work energy theorem. So how does one find work? Okay, force, work done by a force. You have to, let's look at some examples. Okay, case number 1, when the force is a constant force. Okay, it doesn't change magnitude, it doesn't change direction. That makes the integral rather simple. So W from initial to final. How do we solve this? Initial to final, F dot dr. F is a constant, right? You know, when you have a constant integrand, you can take it out of integration. So you take that out. What's left is dr, the integral of dr. What is the integral of dr? You're adding a whole bunch of dr's up, right? So let me draw a little diagram. You can see what that means. Let's say the thing starts from here, initial state, end of its final state over there, and it follows a whatever complicated path to get there, right? So dr is just, you know, you add all these little dr's up, right? Add all these little integral displacements up. But what is the final outcome if you add all these dr's? It's the same as the straight vector starting from initial point to the final point, right? Let me make sure I draw it straight. Right? This is the sum of all these little dr's, right? So that's delta r, actually, delta r. So this is delta r, right? So this is just equal to the dot product of F and delta r. All right? Now suppose delta r goes like this. So this is delta r. And F goes like that. Okay, so that's F. And the angle between them is theta. Then I can rewrite this as F times delta R times cosine theta. There are a couple of ways we can continue with this if you want to simplify this. I can write this as F parallel delta R, or F times delta R parallel. Now, what do I mean by that? F parallel means you look at the component of F along delta R. Okay, so let me do that. That would be you take that F, right? You break it down into F parallel. So this is F parallel, parallel to delta R. Okay, or you can keep the direction of F, but you take delta R, you break it down to a component along F. So delta R parallel is the component of delta R along the direction of F. Either way, right? For example, gravity. Gravity, as you know, is a constant force. So, for example, F equals gravity, which is mg. Okay, so you have an object of mass m undergoing a free fall or projectile motion, whatever. It's under the influence of gravity. It doesn't have to be actually a free fall or projectile motion because the gravitational force does not have to be the only force acting on it. But whatever it is, if it moves under the influence of gravity, you can figure out how much work is done by gravity. Okay, so let's use that as a special case of a constant force. Okay, then I have W I to F. What is that equal to? Well, using the last expression, F parallel delta R. Okay, now suppose or F times delta R parallel. It's actually better to use the second expression because we know exactly what the direction of the force is in this case. The force points downwards. So here's the force, downwards, mg. That's it. That's mg. And then there is a displacement, okay, under the influence of that force. Let's say it moves from here to there. That's the final point, okay? And the motion does not have to be a straight line at all. It can be just arbitrary motion because the gravitational force may not be the only force acting on it. So here's I, here's F. What's really important is to find the component of delta R along the direction of the force. So I'm looking at this expression, okay? So let's find delta R first. Delta R is a straight vector starting from here and ending up there, okay? So that is delta R. What component does it have along the direction of the force? That's the vertical component, okay? The vertical component, that's just H. This distance here, which I call H. The vertical drop, really, okay? That is the component of delta R along the direction of the force, which is vertical. So that is just equal to mgh. It's just that simple. mgh. What's H? H is the vertical drop of the object from initial final state. It doesn't matter how the actual path is, as long as it moved down vertically by this is H. I don't care how it moves along, the XY plane. I just care about what happens in the Z direction, the up and down direction. Okay, because as you move horizontally, gravity does no work. So I don't care how much you move horizontally. What matters when you move vertically, if you go downwards, gravity does positive work. If you go upwards, gravity does negative work. Okay, so this is the expression for the work done by gravity. H is considered positive when it goes downwards. That's when gravity does positive work. And H is considered negative when you go upwards, and that's when gravity does negative work. Okay? So that's one important example of the work done by a uniform, by a constant force. Constantly doesn't change over time. Okay? Another special case of great interest is what happens if F is perpendicular to dr. Okay, what happens if F is perpendicular to dr? Now, in this case, F does not have to be constant, as long as F is always perpendicular to dr. So as the thing turns direction, F also turns direction, but it always keeps 90 degrees away from the object. So let's say the object moves like this, right? So so this is dr, and this is F, 90 degrees. That's F. That's dr. In a different at a different moment, dr goes like this, and F goes like that. So both turned their direction, but the angle between them is always 90 degrees. If that is the case, then clearly W is equal to what? 0, because F dot dr equals 0 when the two vectors are perpendicular to each other, right? It's a special case, but we see that quite often in physics as well. And there are other cases where the force is neither perpendicular to the direction of motion nor constant. For example, the force of a spring, if you extend the spring, you're going to fight the force of the spring, and that force can increase as you stretch or compress the spring further. That's something we can talk about as well. So there are some cases of variable force that we have to deal with. But at this point, we only want to discuss these two special cases. And that will be enough for us to start our application of the work energy theorem. So in our next video lecture, we're going to talk about how to put all of this to use. And that is, using the work energy theorem, can we solve problems? First of all, a simple problem that we have seen before. Do we reproduce the same answer? And we should, of course. Secondly, can we solve problems that are otherwise difficult to solve, something we didn't know how to do before, such as the very first problem that I posed, here, this one, right? This one, how do you find the final speed? Right? Can we solve problems like that? The answer, of course, is yes. When we see how to solve this problem in the next lecture, you will find how easy it really is. And then you will see the power of this new approach. So finally, we'll get back to the solution of the first problem, which I promised we would solve. Right, so that will be in the next video lecture.